subscribe to क्या नाम है तेरे चैनल का?
Today I have with me Rashi Jain. She's an amazing friend of mine and an incredible researcher. She holds a PhD from University of Strasbourg, France. She did her master's in astrophysics and astronomy from Indian Institute of Space Science and Technology, Trivandrum, Kerala. She did her schooling and she stays in Jabalpur, Madhya Pradesh. She is having amazing research paper in the field of astronomy, and she was recently invited for a talk in University of Cambridge, UK. So tune in for this amazing podcast. How's your stay right now in India after having a long, a long sadhana of PhD from France?
Quite relaxing because it's not as hectic. After you have written your thesis, you need a break. And not everyone gets that break, but I got it. So it's actually going very good.
Okay. And what about what else you were missing in India apart from food?
Yes, food and people, my friends and my family. Because when I finished my PhD, by that time, all of my friends have left Strasbourg. I was in Strasbourg, right? So it felt really, you have finished your PhD, your friends are not there. So that part was really something. So I came back to India for people, and that's something I'm really, enjoying.
Okay. What about, tell me something about France. How was your stay during the PhDs? How are the people? And definitely Paris, which every girl, most of the girl crave for.
Mm-hmm.
Yeah.
You have been to Paris too yourself, right?
Yeah, but I didn't like it that much. Where it is like, it's like more hyped as compared to what I see.
It is. You have to be in Paris like in the right weather. You were there when it was very gloomy. I think it was very cloudy and there was rain. Yeah. So France as a country is very, it's beautiful. We all know that. What I enjoyed there was living in a new country where you don't know the language. The people are different. It was an entirely new culture for me. So, in the beginning, there were so many cultural shocks. From everything, you go for shopping, you meet new people at your workplace. So it was very different, but also very good. The work culture there, I really enjoyed working with people over there. They take their work seriously, but they take their off time also very seriously.
Oh.
And the first year of my PhD, and my supervisor told me that, you have 40 days of vacation. What are you planning for your summer vacations? And that was a really good surprise for me because no one has, ever encouraged me to take leave in a workplace.
Yeah.
So I like their work culture, like play hard, party harder. That kind of.
And when I went to Paris, it was like, since the friend who was hosting me sort of, and he went to the supermarket and most of the conversation was like bonjour merci. So means like he was saying bonjour merci. I told him no, he's saying you have to say merci, something like that. I go no, I will say Ronaldo. So he was saying, dude, that is not about football. Okay, it is a greeting.
Yeah, I know it's the pronunciations are not very intuitive in French, right? So when they're saying it was mercy, it is written as mercy, but you say merci.
Oh.
So yes, learning French was a very big challenge for me. It still is.
Do you
I
know
can converse
French now?
a little bit, like I can get by in a supermarket or like absolutely necessary job.
Okay.
Could be get done, but otherwise I cannot converse in French. So I just learned like for survival. That was fine.
Okay. And tell me more about Strasbourg. I see some of the picture. It's like far, means like a beautiful kind of small town.
Yes.
Yeah.
It is actually. So Strasbourg is capital of the region. It's called Alsace or Grand Est. And that part is like the most beautiful part of France, which I did not know because I have not seen more of France. But when people told me that this is the richest and most beautiful part of France, it actually shows. You might have seen Disney movies like Beauty and the Beast and things like that. So a lot of these towns and these castles are inspired from Strasbourg and nearby hamlets. So it's actually, Strasbourg has very rich cultural history. It's between Germany and France. So there was a point where it used to shuffle between Germany and France during World War.
Oh,
So people will wake up and they won't know whether they are in France today or in Germany. So that
okay,
was quite interesting. The mix of culture there. The language is called Alsatian, and it's not French, it's not German, something in between.
okay,
The
okay,
food
okay.
is also different. So we wouldn't know because we don't know France, but French people knows the importance of Strasbourg. It's a very interesting place to be, yeah,
Okay.
to live.
T- Tell me more about your PhD topics and what you research on.
The important
Yeah.
things, yes. So
Yeah.
I was doing my master's in IIST, and
Hmm.
there I was working with my supervisor, Dr. Sarita Vig,
Yeah. Hmm.
and it was in ultraviolet. India's first space telescope, AstroSat. So we acquired data from that for a globular cluster, and we were studying the
Hmm.
hot population of globular cluster. So
Okay.
my first
It's like a star
experience.
cluster.
It's a star cluster, yes. The globular
Okay.
cluster is a very old star clusters where,
Hmm.
so what happens is stars all form at the same time
Hmm.
in the same cloud, right?
Hmm.
The stars that continue to stay together, they form a globular cluster. Some of the stars
Okay.
fly off and then they become field stars like our sun, for
So they
example.
have the similar age in some or
They have
other
similar
ways.
age, yes. They have
Okay.
similar ages, they have similar chemical compositions also because they
Okay.
were formed from the same cloud and
Okay.
very peculiar properties. So, yes,
Okay.
my field of study is globular clusters,
Hmm.
and in astronomy, you can either do observational or theoretical, and mine
Hmm.
is more towards observational. Like, I take the data from the telescopes and I analyze the data
Okay.
and deduce what's going on.
Okay. What would be the interpretation and all? Means like what you interpret from those data which you collect from telescope and all.
So it depends because we collect data across entire spectrum of like an entire
Light. Yeah.
spectrum of electromagnetic waves,
Electromagnetic.
right? Yeah.
Yeah.
So right from infrared, optical,
Hmm.
ultraviolet, and towards higher frequency, gamma rays, etc.
Hmm.
And my field is like towards higher wavelength side. So I have studied
Okay.
in infrared, in optical, and in ultraviolet. These are stars.
Okay. Okay. Okay.
So you can study different properties depending on which range of spectrum you are in.
Hmm. Okay.
But if you ask for myself, at first in my masters, I was studying the very hottest stars, and in my PhD, I moved towards the colder ones. So I was studying near infrared properties,
Hmm.
and I was not studying individual stars. I was studying globular clusters as point sources of
Okay.
another galaxy cluster.
Okay. What do you mean by hotter stars and colder stars? Is it about the temperature and all? How do you
Yes.
define some star as hotter? Because everyone will be hotter as compared to what we feel in on Earth. Yeah.
So
Yeah.
it's an interesting question. Like actually, in terms that I'm talking about, hotter actually means very hot stars. The stars have surface temperatures. They have
Yeah.
multiple layers, and when we talk about temperature, it's always the surface temperature.
Hmm.
And this depends on how the star was born. What was its initial mass when it was born? Because
Hmm.
so what happens is there is a large molecular cloud, okay, gas and dust,
Hmm.
and there comes a point in its evolution when the mass and the density reaches a limit where it starts to collapse under its own gravity. That's how the stars are
Okay.
formed.
That's
But the molecular cloud is so giant that it does not collapse into one
okay.
big clump. What happens is there are smaller clumps forming.
Hmm.
So there are it's called local collapse.
Okay.
So from one molecular cloud, there are multiple stars that forms,
Okay.
and there. When we talk about stellar timescales, they are in a range of millions years. So when I say
Yeah.
similar timescale, I'm talking about million years, right?
That's true.
And these stars, they are formed around the similar time span. But
Hmm.
what is the difference between these stars is their masses. Some are formed massive, some are less massive, and
Hmm.
this decides how they will evolve
That's true.
because
Yeah.
the evolution
Hmm.
the speed of evolution depends on their mass. So the stars which are very massive, they evolve faster than the
Hmm.
stars that have a smaller mass at their birth. They evolve
Hmm.
very slowly. right?
Okay.
And then it depends on which stage it is in. So the star, when it is burning hydrogen, it has certain temperature. When the hydrogen is finished, it starts to burn helium and
Yeah.
subsequent elements. The temperature
Yes,
also
yes,
changes, the
yes.
brightness also changes.
Hmm.
So when I talk about temperature, I actually talk about surface temperature.
Hmm. Okay.
And in my master's, I was studying hot stars. They were in like late stages of their evolution. They are called horizontal branch stars. So their hydrogen is finished, and now their helium envelope is exposed, and that's what's
Okay.
burning. And
Okay.
that gives them very high. For example, the temperature of our sun is around 5,600 kelvins,
Kelvin,
and
yeah.
these stars that I'm talking about, their temperature ranges from 10,000 to 50,000 kelvins. So that's why they're called
Okay.
hot stars.
Okay, I got it. One question I was thinking about when you were parallelly giving me this concept about from one cloud how different stars are formed. It appears like if I drop some water and when it passes the ground and different kind of size of other water things comes out, and like it appears like I was having that interpretation in mind how a similar thing can happen in nature in India also, but there'll be different forces involved everywhere, I would say.
Yes.
So what all facility you have, you were mentioning about data collection, so they would be telescopes. And what are telescope means, like how they operate generally? It's like a lens which we see, in childhood we used to do like to burn a paper, we used to use lens because it concentrates light at a point, similar like light is an information source in some or other ways.
Yes.
So in that way, how means like how you scale a lens to a telescope and how it observes the universe and all. Yeah.
So yes, there are when I talk about data collection, it's usually from the telescopes, and like I mentioned, you have the entire wavelength spectrum of wavelength to observe from. So, for example, if I want to observe an object in X-ray, the telescope would look different than an
Oh,
optical telescope, for example.
okay.
And it's exactly what you said. You have a lens, and it focuses the light from an object, and so it's a very simplified explanation of what a telescope is, because these are huge telescopes. Most of these operate from Chile because it has the cleanest and the
Okay. Sky, yeah.
driest atmosphere, so it's very easy to observe there. So a lot of these telescopes are in Chile, and that's where I got my data for PhD from.
Okay.
So it's an infrared and optical, but yes. So there are so many factors that goes, like our atmosphere. It is opaque. It is opaque to everything else, but optical and some parts of infrared and radio. So if you want to observe in ultraviolet or X-ray, for example, you have to go to space. So there are all these space telescopes.
That may be due
And
to ozone and all the protective layer we have. That's why it's opaque
the
and all.
atmosphere, yes, the atmosphere does not allow like it's good for humans, but not good for
Yeah.
astronomy. So you have to go to
Yeah.
space.
Yeah.
So you can observe radio from the Earth, you can observe optical from the Earth, and a part of infrared from the Earth.
Okay. Okay.
And yes, atmosphere is like an obstruction because it keeps changing, and it makes the data worse. So if you go to space, you
Okay,
get like a
okay.
better quality of data. So that's a
Okay.
plus. So there are, yes, different kind of telescopes. Radio telescopes are larger, are like they're very different from optical telescope. They don't have a lens, or because radio wavelengths are itself very, the wavelengths are in kilometer range.
Yeah. Yeah.
So you don't need a small size lens. You need like big. You
Bigger.
might have
Yeah.
seen those
Very giant.
they're actually called giant meter wave telescope, and the
Yeah.
name says it all. So
Yeah.
there are like kilometer long fields. In India, for example, there is GMRT, Giant Meter Radio Wave Telescope.
In where?
So
Ladakh? Where?
no,
Yes,
it's in Pune.
okay. There's something in
Pune.
Ladakh also. They were talking about
Hanle,
constructing
yes,
one in Ladakh. Okay.
There's already one, the optical telescope in Ladakh. And
Okay.
yes, it's used remotely. It's accessed remotely from Bangalore, I think. Yes, and you can get optical data.
And it means like I agree with you. Like the diameter of the, I would say, antenna or the collector
Yes.
tells about how good it is. Like whenever we hear about news, okay, China is constructing 60-meter wide. Means like something like that. So you understand, okay, it's bigger, it can collect more information, and you can process more. So more about telescopes. They recently, like, much more limelight related to NASA when they launched from a company, with the help of a company, they launched James Webb Telescope. It's like the same concept to have more pure data. How this telescope, in terms of quality and accessibility of the data, how it is like different from, I would say, that are on Earth. That is true. One of them could be atmosphere, and what could be other thing?
So, okay, first I'd like to tell you about there are two things when we are looking at data. First, you want the data to be very sharp, the resolution, the better that, because imagine you're looking into space. There is like a very small part of sky that has millions of galaxies, right? A
Yes,
small
yes,
part
yes.
of sky.
And
You
that
want
will
them to be
appear onto
resolved.
that appears on few pixels of
Yes,
the image. Yeah.
of your detector.
Yeah.
So it depends on your telescope how well it can resolve these objects.
Okay.
These are
Okay.
very small objects, and you want to be them to be resolved. First thing. Second is the magnification, the magnification power of your telescope. So the depth, how deep into the space can it go? So what happens is in space, objects can be faint or bright, right?
Oh.
And we talk in terms of magnitudes, and these are the numbers, just like 1, 2, 3, 4, 5.
Yeah.
And the higher the number is for an object, the fainter it is. It's non-intuitive, right?
Okay.
So stars, for example, you see stars in the sky. Some of them are very bright, some of them are very faint, and you can be for sure assured that you're not looking at all the stars in the sky. There are so many stars which are fainter for your eyes to be seen, and the same
Okay.
goes for telescope. So a good telescope would have the capacity to look for very faint signals as well, to be very sensitive to these faint signals.
Okay.
So
Okay.
these are the two factors that decides how good a telescope is. First is resolution, second is how deep into the sky it can go. And if you're on Earth, atmosphere plays a very huge role in both of these factors. Atmosphere obstructs the light, so you can't see very faint objects. Second, it also makes the resolution bad. There's
Yeah.
only an upper limit where you can achieve the resolution, after which you cannot go. But if you go
Yeah.
to space, sky is the limit.
Yeah. Yeah.
So James Webb Space Telescope Hubble Space Telescope was like the predecessor of this one, and it entirely changed the field of astronomy since it was launched.
I think some of the research were related to Hubble got a Nobel Prize also. Is it means like, no, somebody got Nobel Prize out of Hubble telescopes? This one was like our universe and the star and all. We are, they are accelerating farther from each other, that somebody has seen in the data, like all the clusters and stars are moving farther and faster away from each other, or means our space is becoming more stretched in some or other ways.
Yes.
Yeah.
Yes, I think you're talking about the expansion of the universe. That was a Hubble's discovery. That is true. That is like a groundbreaking discovery. Because initially we did not know how the universe was born. There were so many theories. But after this, people were so sure that there was something like Big Bang that happened, after which the universe started to accelerate. It's a very interesting field in cosmology, where, study how people came to this conclusion, and, how well do we know the speed of acceleration of the universe and all of that. Very interesting. And yes, it was discovered by HST. But HST also has its shelf life, so it's going to, stop working at some point. And before it does, we need to launch something better. So James Webb Space Telescope is the successor, and it is much better than HST. Okay. That means it can go much fainter in the magnitude range to observe fainter objects, and the resolution is also better. And one more thing was, James Webb Space Telescope was also made to what you said right now about the expansion of the universe. So what happens is, as a result of expansion of the universe, when you are looking farther away, you're basically looking into the past, because these objects, so, and also because of expansion, what happens is, like, it's a very technical thing, but just as a fact, you have to accept it, that when the farther you look, in this spectrum, you go towards higher wavelengths. So, like, if I look in the vicinity, I'll see objects in optical lights brighter, but I go farther away, infrared is better to observe these objects.
Okay. Okay.
So James Webb Space Telescope is primarily for infrared because we want to look much farther away in the universe, and it has it's launched last year,
Yeah.
and it's already making breaking
Breaking.
discoveries, and
Yeah.
it's just like in the initial testing phase, and we cannot imagine what it will bring when it's like fully functional and there's so many things happening.
I remember like when this news came, like there was some groundbreaking research happening or groundbreaking data coming out of James Webb Telescope. They were talking about installing some similar telescope on moon also. So NASA was thinking of doing that via gateway and all these other things, which I also work on. Yeah.
Yeah. Oh, okay.
Yeah.
So was it like optical telescope? Because what I heard last was a contemplation of a radio telescope.
Okay. No, I'm saying in terms of whatever is built on moon, if you're trying to build something on moon, we are trying to build habitats on moon. That is for long-term human existence over there, to do research and all, similar to International Space Station.
Yes.
So there were similar things coming in our group also. It means like that. If some news comes out, so if it is related to us, that is also pointed out. So one of the things which intrigued me while you were mentioning about the expansion of the universe, means like right now, if we are expanding so faster, so what will happen in the future? We'll be like, right now we are seeing some stars, they'll become more farther away from us, more farther. So we are going I think we are going into some form of aloneness in the universe. Means like, since everybody is going farther away from us, and for example, this human civilization dies after some number of years, there'll be similar ice age or whatever happens, new human kind of intelligent being arrives or similar of that sort, according to evolution. So they will be looking at if they are sufficiently advanced enough, and they are again looking at the stars using the same technology we build. They may be building their own. So they may be thinking, okay, now this galaxy is that much farther away from us. Like it is so fascinating to see how smaller our time scales are actually.
It is, yes. Yeah. Like you said, right, if some other civilization comes, so I am just thinking about time scales. The expansion is happening, but it's very slow as compared to our time, like our lifespans. Okay. Even the lifespan of the entire human civilization, like 2,000 years, 4,000 years is just nothing. Yeah. So even after 10,000 years, another civilization comes and they start to observe, they'll observe a very tiny change in the... But there is a video on YouTube, it's like a half an hour video where it shows how the universe goes from Big Bang to, eventually when everything will be so farther apart that it'll be like dead. And even though we won't exist in that time, in that time frame, but it's just a little scary to see the universe die. And I think everyone should watch it just to get a perspective on how small we are.
Yeah, also in terms of, for example, in previous, maybe some 1,000 years ago, some million years ago, there may be a probability that Mars may have there are theories related to Mars having a technologically advanced civilization. There is a theory about that. The theory says that there were two technically advanced civilization over there and both nuked each other. Because people see, this is a proper theory, people believe that this happened. There are few theories, like there was existence of human on Mars. For example, if they are some billion years apart, in past, they may be, if they are technologically sufficient, they are also looking at the sky, because human started looking at the sky and navigation is sky actually previously. So they may be thinking some other form of universe, if they are if they are billion, I don't think they are billion year apart. Maybe if they are million year apart from us in the future, in the past, so they may be seeing some different universe than what we see.
I also imagine something like that if there is another life form and if they are like million light years away from us, what they would be looking at, maybe dinosaurs or nothing. Yeah. And the same thing, we are also looking at like the past. So we don't know if something exists right now on some planet which is millions of light years away from us.
That makes the research more challenging, I feel. If you are talking about 1.4 billion light years apart a star, means like right now it may not be existing at that point of time. There may be something else. The globular cluster you are talking about, that may not be at this time that may not be possible over there. So it's like how space and time are related, you know. Sometime if I want to go from here to India, so I talk about this much time will take. Okay, because there is a space in between us. Similarly, that happens when we talk about 1.4 billion light years apart. We talk about time, they may not be existing at that point of time. It's like how time is so relative, you know, that
Yeah.
in physics, that's the obvious
I think
thing.
there are
Yeah.
so many constraints. One
Yeah.
is time, like you said, that
Hmm.
we are separated in time, so
Hmm.
maybe they do not. If they exist right now in the same time
Hmm.
frame, they will, or we are looking at as past, so we might not observe that. Plus, we
Yeah.
don't have technical capacity that you can see the exoplanets and the stars, but you cannot resolve these stars. I mean, even the closest star to us, Proxima Centauri,
First
we
century. Yeah.
cannot resolve it.
Yeah.
What the star, everything we know about a star is from, like, most of it is from sun,
Hmm.
and the other stars are still point sources. So I cannot
Hmm.
imagine if there is a life form existing, we can just observe it with our telescopes right now.
Okay.
But like Carl Sagan said, absence of evidence is not evidence of absence.
Yeah.
So maybe there is something out there, we have just not observed it, or
Yeah.
come in contact with it. I'm not saying there is, but there is a possibility.
Yeah. You mean to say there is one more fact I was reading, or I watched a video in which it was showing there was some video like they have collected some amount of data, and during that tenure of data, they have seen like one star was there few years back and it was not there after few years.
Which one are you talking about? Because there is you know the constellation Orion.
Yeah.
So the shoulder of the Orion is Betelgeuse, the star, and that was the star people observed. Like, I think last couple of years, it suddenly became very dim as compared to
Oh
its usual
yeah.
brightness.
That's what I'm thinking.
So
Yeah.
that was very surprising because we were not expecting that. But then
Hmm.
it turns out that the star is in its last stages of life, and
Okay.
very fascinating fact that it can go a supernova anytime.
Okay. Okay.
Now, but any time in astronomical scales can mean any time from now to next 2000 years. So
Yeah.
if we are lucky, we'll get to see it in our lifetimes. Otherwise, our children's will.
Yeah. Or may not be. Or more advanced civilization than Homo
Yeah,
sapiens. Who knows? And
maybe.
apart from that, let's talk about like our sun, which seems very brighter and very bigger in size, but in compared to other stars which are existing in even in our Milky Way, I don't know how many number of stars are there in our Milky Way, but I can approximate it like 80 billion, something like that. It's in billion numbers or in millions, something like that,
I
right?
think
Because
it's in scale of millions, but
yeah,
that's also a lot.
yeah. So there is a higher probability that there'll be a planets around it, and there'll be a.
Hmm.
So there is a Drake equation. Drake equation
Yeah, yeah,
talks
yeah.
about number of civilization in the Milky Way based on what is the distance from their star to their planet, and how many have them sufficient, things to have a life
Yes.
form, and how much possibility that life form will reach to a level like human being, and what is the probability that number fraction keeps on multiplying, so it becomes a very small probability. So that is about Dirac equation. But the question I wanted to ask about is the sun. How sun is different from other stars in our Milky Way, and what is the size, and what is intricate details about sun which makes it different?
Okay, so first let me burst the bubble for you. Sun is just a very regular normal star. There is nothing
Okay.
special about Sun. It's only special to us. And the thing that you're talking about, Drake's equation, I think there is for all the stars, there's something what they call is as zone. I forgot the name, but it comes
Yeah.
from that story of this girl who goes to Teddy Bear's house. What's the name of this
Yeah,
woman?
yeah. There's
So
some
it's a
zone. I don't remember, but I will put it in the video right now.
Yeah,
Yeah.
it's a Lilliput, not Lilliput, but something with an L. So that zone. And it's like at a perfect distance from the star, not too far, not too close, and it
Yeah.
depends on how big the star is, what's its temperature, and all of that. And that zone is where, if a planet is
Goldilock.
found, Goldilocks zone, yes, thank you. The Goldilocks zone. And uh, where that's the zone where if the planet is found, there are more chances of it
Okay.
hosting a like a carbon-based life like ours.
Maybe that's because
So
of the water. Water will be available in
yes,
the
whatever.
form of
But
liquid. Yeah,
it's unfair for us to expect that the life, in other parts of the universe will be in the same form as us,
yeah, that's
ours.
true.
It could
That's
be
true.
something else, right? They might not
Yeah,
need water at all.
yeah.
So yeah. But you are asking about sun, that if sun is
Mm,
special. So sun is not a special. Sun is in fact a very normal, very like relatively cool star. We have
mm,
when we talk about star, we classify them based on their size and their temperature. And
yeah.
the classification, we have names. It goes from O, G, O, B, A, and
OG.
all these things. So G, our sun is the G. 5 kind of star. G is like in terms of size, it's
Mm,
very small, and then 5 is like temperature. Temperature is relatively low.
okay.
So yeah, the sun, but it works out, right? If it were too hot, maybe we wouldn't, like, the life on earth wouldn't exist, or if it were too
Mm,
cold, in
mm,
same case.
yeah.
So it's like probability, to host a carbon based life form, and it just worked out in case of sun.
Mm,
But that doesn't mean we are special, or sun is a special, or we are at a special place in the galaxy. None of that.
yeah. Yeah.
It's just a, you know, coincidence.
That's true. Or probability, much more mathematical term. So
Yeah.
about sun, I read about the sun, and the first thing the thing when I used to have physics in my 11, 12, the number which stuck in my mind is Chandrasekhar limit, because
Hmm.
Chandrasekhar was like Indian. It's like a star will convert into a black hole if it has mass of 1.4 times of our sun. Is it the 1.398, something like how? That's
1.4. What happens is it collapses and it becomes a neutron star.
or even a black hole.
It can become a black hole depending on the initial mass of the star.
Okay,
So
okay.
very massive stars, they collapse and become black holes. But if,
Mm,
like, there are limit to masses, a
okay,
less massive star will become a neutron star.
okay. So it means if the mass of our sun, the mass of a star is 1.4 times of our sun or more than that, once it, depletes its hydrogen based or helium based whatever energy source, it will become white dwarf or
Dwarf,
neutron
yes.
star or
Yeah.
maybe a black hole.
Or
So
maybe a black hole, yes. It
okay,
depends on the mass,
what about means
initial
like
mass.
sun? Even NASA is putting a lot of effort, even India's Aditya mission related to solar Parker probe, and which is going towards the sun and finding out about corona
Yeah.
discharge. Which, so there is one intriguing fact I came to know about sun is like our atmosphere also has troposphere, stratosphere, mesosphere. They have photospheres, chromosphere, and one more corona. I realized
Yes.
that the temperature of corona is much
Yeah.
higher than what's inside, means like photosphere and chromosphere. And what's the point of studying those? I would say corona. What is the relevance of putting so heavy, I would say, economically costly object into over there and passing it over the corona? And what's the objective? I believe.
I think first is curiosity, because, like you
Mm,
said, it's like the outer layer of the sun, out of photosphere, and it's still the temperature of the corona is
mm,
higher than photosphere of the sun.
okay.
And by temperature, we mean the kinetic temperature, right? The particles,
Mm,
there are, it's
yeah.
not temperature, it's that
That's a,
temperature. So the
yeah.
particles are very high velocity, and then
Mm.
that
Yeah,
temperature
but
is
because
higher than.
that temperature is also, we talk about kinetic theory of gases,
Yes.
3 by 2 kT and kinetic energy, and you find out the definition of temperature from there, from kinetic theory of gases. Yeah, you were talking about the temperature and corona and all.
Yeah, but what is relevant to us is these coronal mass ejections that cause solar flares, and sun has its own cycle of, I think, 11 years, where it goes through a minimum and maximum of activities
Oh.
on the sun. There are sunspots, and it all affects us, the life on Earth. Eventually, it will, right? We have a magnetic field on the Earth which is protecting us from these
Yeah.
ejections from the sun. But we need to know more about it to be able to control if something more extreme happens in the future. We need to
Mm,
know basically what's going on, because sun is important to us. Everything else is
yeah.
curiosity, other stars, but sun, what happens on sun affects us. affects everything. Like we have set up the network of satellites and everything. And if there is a solar storm, it will affect all of this. It might even shut down. We have to start from scratch everything again. I'm just saying
Yeah.
something like that. If something extreme happens, which is not going to happen, but you need to know the magnitude or amplitude of these things which are going on. And the second is, of course, curiosity. Even though sun is the closest star to us, we don't know a lot about it. There is so much. It's still a mystery.
Yeah.
So, you know, we can study all the stars, but if we have one closest to us, it's important. But so far it has been challenging because sun is so hot and everything that went near the sun, it couldn't,
Yeah,
survive for
survive.
very long. So we are just trying to make more durable objects, more durable missions. Like you mentioned, India is working on Aditya mission, and then there is Solar Parker probe. So
Yeah.
all of these are very exciting opportunities for us to know more about the sun.
That's true. And one more thing which I would like to add on is like sun is the most fundamental thing for survival of any possible living being on earth. So if we see we eat food that comes from plants or if somebody is you are vegetarian, I believe, and if somebody eats non-vegetarian, then that animal also in the food chain, it's related to the plants, and for plants the most fundamental thing is sun. Apart from that, from technological point of view, technology depends upon the way we save our, I would say, electromagnetic technologies in the lower Earth or the higher Earth orbit. It's having this magnetic shield. Even auroras are also is a after effect of, or I would say the effect came due to the magnetic interaction of magnetic field and solar mass. Yes.
Particles from the sun, yes.
Yeah. But the thing which I was recently reading is how NASA's Solar Parker probe is touching the corona. I was reading this amazing video in which they are saying that it is entering into coronal discharge. They have made the orbital mechanics like this. So what happens in orbital mechanics, whenever you want to do a transfer to some other planet or star, there is a thing called Hoffman transfer. So you have to insert a velocity from a point so that it can go to another star or planet. So that's how we also reach onto other planets. Have minimum energy transfer. So they were talking
about very interesting phenomenon. It's called like in more layman terms, it's called gravitational catapulting. I think that's what you're talking about.
Gravitational catapult or gravitational assist.
Yes,
these are all the things. Means like,
because I remember this from when we were launching this thing to the either Uranus or Pluto. I don't remember, but to very end planets, and we were using the gravitational field of Jupiter to catapult it to so it took like 2.5 years less for it to reach that planet than it would have taken without the assist. So,
apart from that, the size of the probe, the size of the entire setup will be less because you have to use less fuel. Visa payload also reduces. Apart from that, I think it was Voyager, and there were some initial missions who used these assist. Voyager already crossed the solar system, I believe.
It's like we don't know what the edge of. So I think it's on the edge of the solar system.
Somewhere on the edge of the solar system. Let's get back to this Aditya mission I was talking about. This NASA Solar Parker probe. So the difference which I see when I was reading about this is like NASA's Aditya mission is on L1. Means like Lagrangian point. It will be revolving around the sun to study corona and mass ejection and all. However, the technology of NASA, I won't say because of the funding, huge amount of funding, they are entering into this, 50 years ahead, nobody thought of. These were concepts existing, but nobody thought of entering into this coronal injection. So they are like very intricate orbital mechanics around it, and they are properly measuring it. Nobody knows why the temperature of corona. It's the Nobel Prize kind of a discovery if somebody does that. Why corona? What are the factors that makes corona very high temperature, like 60 or 70,000 Kelvin or something in temperature, degree centigrade? What makes it so hot? So that is a Nobel Prize kind of a discovery. So what about the Aditya mission? How, when it is launching and all? I don't have the timeline as such.
I also don't think, but like in next 5 years they plan to. But the thing with these missions is we can only have a timeline. For example, there is a mission called Euclid,
Oh.
and it was supposed to launch like in 2021, but it's
Hmm.
2023 now, and it's still in the pipeline because so much have happened because it was going to be launched from Russia, and now Russia and Ukraine are at war.
Hmm.
So
Hmm.
all of that. So yes, I think we can expect it to be launched in next 5 years.
And other thing also, there are particular dates on which you can launch because of your orbital mechanics thing. Like for I believe there is a documentary on Mangalyaan. They were talking about if we miss this date, we have to wait for 6 more months because that orbital mechanics things works like this. So Mars should be at a particular position so that when we do a Hoffman transfer, it should whenever our Mangalyaan reaches there, then it should have a orbit over there. So there is a particular dates. If that date misses, like 1 year misses, and
It's
cover.
possible, but I think it's because you were sending this to Mangal and there have to be a line, and I am
Yeah,
the wrong person to ask about mechanics. But
yeah.
if you are launching satellites, I don't think it's that sensitive to dates as such. Yeah.
Depends on means like if you are very particular about like India was very particular about minimum budget,
Yeah.
minimum energy requirement and anything. So however that's why we purposefully stick on to Hoffman transfer, whereas NASA mission that they doesn't care about because they have very heavy rockets and very advanced technologies, so they don't care about when Mangal is at that position or not. So they just
Yeah.
enter means like
So I
don't care
think for
about.
Aditya L1 mission also, if that has to be sensitive to dates as well, right? Because you are
Yeah,
launching, you might be
yeah,
using Hoffman transfer to
yeah.
launch it into the required orbit near the
And
sun.
the story of Mangalyaan is like, it was very funny when Narendra Modi was mentioning about like it takes going from Earth to Moon is less than it's if you go in Ahmedabad 10 rupees metro and going from somewhere to somewhere is like 10 rupees. People were thinking it exactly means like, okay, I can take an auto and go to Mangal if it is so cheaper.
Oh my God.
These
That's
are
why we
just for
need more
numbers.
science communication, I think, in
Yeah.
India. We're
Yeah.
missing that.
Because maybe to make people more
Yeah,
understanding
to
like
make them understand.
how cheaper it is, and but however it took a limelight of a lot of international media that how cheaper the budget of
That is true.
yeah
Like ISRO does things very economically. You
yeah
know, when you look at other countries, like how they launch these missions, and
yeah
the budget is really, way less than what they use, and
yeah
we deliver. So
yeah that's true.
that's an achievement.
So let's see. And so whoever gets the corona thing, physics of it, and with proper thing why the temperature is so high.
Yes.
There is some relation with magnetic field. What are the localized magnetic field and how it increases the temperature
True.
and what is the flux around it. So maybe India are also trying. Hopefully,
Yes,
with
I think
Aditya
the
mission we can
magnetic
get something.
field of sun is very complicated topic. Like if you
Yeah.
just go on to reading, we have very like it's not very long ago that we came the guy Parker, I don't remember his first name, but he was the one who basically studied about the solar winds, how these loops are formed, and the
Yeah.
magnetic field, how it is related to the surface of the sun. So it was just a discovery of what is going on, and now why that magnetic field, what
Yeah.
other things magnetic field is driving in the atmosphere of the sun. That's something we will need to find out with these missions, perhaps.
And one of the thing which about sun is sun and Jupiter. I don't know about Jupiter, but sun is just a bowl of gas. A lot of people thinks like there will be a solid surface beneath somewhere down the line and it will be like gases after that, maybe a thicker atmosphere, and somewhere down the line there should be somebody, a solid core, but it's like totally gaseous. Like how Jupiter and sun are similar, but Jupiter is that diplomatic person who is stuck between two people. He wanted to be a star, but due to some factor he became a planet. Yeah.
No, actually, yes, that's a misconception. There is something called so there are different kind of stars, right? And
yeah.
white dwarfs, red giants, and stuff. There is something called brown dwarfs, which we have discovered very recently. And these are the stars which are called failed stars that were like that could have become stars, but because they did not have sufficient mass, they became a failed star. What
Yeah.
happens is initially the star has two kind of forces: the gravitational collapse
Uh,
that gives its energy, and
Electron.
then at some point nuclear fission starts
Yeah.
to ignite the core, and
Yeah.
then
It's
whatever
a
happens.
nuclear sends it outside and gravitational pulls it inside. Yeah.
Yes.
Yeah.
So a brown dwarf does not have enough mass to ignite the fusion inside its
Mm.
core. It just collapses under its own gravity, and that's the only thing it has. But
Okay.
Jupiter, as a matter of fact, has like much less mass than a brown dwarf. So
Hmm.
it's just a planet. It's not a failed star.
But
But yes, I
however,
can imagine. It's so huge and it's also gaseous, so it's
yeah.
natural for us to like for someone to believe that it could be a failed star, but that's not
Yeah.
true.
Okay.
Jupiter is just a planet.
Okay. And about the Juno mission, they
Mhm.
also, NASA's Juno mission, they went into Jupiter and trying to study those gases and all. I
Yes.
don't know. Nobody knows yet whether there is a solid core available or not in the Jupiter,
Yeah,
or
no,
it will
we
be a
don't know.
purely
Yes,
gaseous. Yeah.
yeah,
So who
because
knows?
who knows?
There
Who
may
knows?
be
Yeah, that is true.
things
But
change. There
that's
may
the
be
thing.
new types of star which will like, okay, this guy is between planet and
Perhaps Pluto
something.
was a
It's
planet once, so we don't know. But
yeah.
there are like these definitions are made by us, so
Yeah.
yeah, we don't know.
However, Jupiter plays a very important role in our solar system.
It
Its
does.
magnetic field helps us from the coronal discharge and all. Yeah, Jupiter's
Jupiter's. So
yeah,
maybe I'm not sure about that part, but it does
hmm,
because it's like the heaviest planet. After Sun,
yeah,
it's the heaviest planet. So
hmm,
um, in field of planetary science, we talk about how the planets are formed and how but the
hmm,
solar system is bound together.
hmm,
So if you know that now there are 8 planets.
hmm,
And initial 4 planets are rocky planets, like they have solid surface. Mercury, Venus, Earth, and Mars. We are
hmm,
4 planets, and in this zone, we are all rocky and small planets. And when you go farther away, these are Jovian planets or gaseous
hmm.
planets. So all these have like
Oh,
gaseous surfaces. So that's a very in terms of planet formation. When you talk about when the star was forming, so from the debris of stars, these planets were formed,
okay,
and how the angular momentum is basically where the sun is, and most of the angular momentum lies with the sun, and the rest lies with the Jupiter. So the other planets has basically none. So it derives the
yeah,
dynamics of the solar system and all of that.
hmm,
So yes, Jupiter does play a very important role in the whole
hmm.
dynamics of our solar system.
And about one thing also, like if you remember in this movie Interstellar, they talk about this red spot in Jupiter
Hmm.
where they
Yes,
enter from, and I don't know what was that. It was a wormhole where they
wormhole.
enter.
Yes.
It enters into. Then they talk about Gigantua, where it was a black hole, and the black holes are also very intriguing. I believe means like it's cosmology and your astrophysics. There's a lot of people who study about black hole, and what are these means like to have much more discussion about that. What are the fundamental things about black hole? How a star converts into the black hole? That is the one of the thing.
So black hole is the end stage of a very massive star. Eventually, a star collapses, like when its fuel is all exhausted. There
Hmm.
are very complicated multiple stages that goes from main sequence of a star to the end stage of a star, and everything the star goes through in its lifetime is derived from the fact what mass it had when it was born, and
Hmm.
one more factor is eventually if it was in interaction with another star. So did it like it accreted more mass, or did it give away its mass? So depending on that, a star can become anything at the end stage. So if it's not massive enough, it will become a white dwarf. If it's slightly more massive, it will become a neutron star, and if it is even more massive, it will collapse into a black hole.
Okay.
So black hole is nothing but a very dense state of like, I mean, I'm again putting it very simplistically. It's not that simple,
Hmm.
but a black hole is very dense state of like the matter from which the
Yeah.
star is formed, and that's what happens. Like white dwarf is itself very dense. Like you have compressed the mass of the sun into something which is I don't know the size of the white dwarf, but let's just say for example, I don't know, 300 kilometers or something radius. I'm not sure. This
10
is just
miles.
a 10 miles. But no, 10
Yeah.
kilometers. Okay, 10 kilometers is for a
10 miles.
a pulsar. A neutron star is 10 kilometers radius.
Okay.
10 kilometers is very small, and the mass it has is much higher than the mass of the sun. So you
Yeah.
imagine how dense we are talking about. And for black hole, that becomes 3 kilometers. 3 kilometers, and the mass of the, not the mass of the sun, like 100 times the mass of the sun or something like that. So it's very dense. Even light can't escape. Nothing can escape a black hole. And that's why it's black, because you can't see anything coming out of it.
Yeah.
So something is black, you cannot observe it. But in 2019 or 2020
Yeah.
was when we saw a black hole for the very first time, and I think it's one of the biggest achievements in the field of, like, recently in astrophysics, to be able to observe a black hole,
Yeah.
which I never thought we could image also. So I'm not an expert in black hole, but I agree it's a very interesting topic. There goes very complicated maths and physics for people who study. It's mostly a theoretical field, but nonetheless very interesting.
And apart from that, they clicked a picture of black hole, which was at the center. They didn't click anything. It was event horizon, which they pictured out. And they were talking about the algorithm, which was developed by a woman or a lady
Computer
in MIT.
scientist, yes.
Yeah, computer scientist, where it collects the data from different telescopes.
Yes.
And this algorithm we generally call a reconstruction algorithm. If you take
Okay.
data only from one telescope, however, if you manage to collect data from different kind of sensors and you deploy a reconstruction algorithm, you will get much more better representation. It's like using one eye versus two eye versus
Okay.
third eye. Okay.
So I
if
did
you
not
are-
know the technical details. Yes.
Yeah, so it was very fantastic from the point of view of a, engineer, because these are reconstruction algorithm and these are
Yeah.
pretty good images. After that, they did some, I would say, some sort of more filtering of the image to have much more. There were multiple levels of algorithm, I believe.
Yeah. But also, just to mention that it was a radio image, it was not an optical image. So,
Yeah.
and in radio it's possible because, so what happens is the resolution of a telescope is inversely proportional to its size. The bigger the telescope is, the smaller you can resolve an object. And the advantage in case of radio telescope is you can make it kilometers large. So even Earth can be a big telescope if you have one antenna on one part of the Earth and second antenna on the other part of the Earth. That becomes your telescope. So I
Yeah.
think they used ELT for making these images. And this black hole was actually not at the center of our galaxy. It was the center of MET7, which is like 50, if I'm not wrong, 54 million light years away from us. So we have imaged that black hole. And I think the other one, which is in pipeline, is the black hole at the center of our own galaxy.
Yeah. So at the center of every galaxy, there should be a black hole. I don't know the theory behind it. Maybe because is it possible that all the, galaxies are revolving around, all the stars are revolving around a common center point, and since it need to be very highly supermassive in terms of its gravitational field, so there must be a higher probability that there will be a black hole over there.
Actually, no. Not all galaxies have a black hole at the center of their at their center. Some galaxies have black holes. Some have something called AGN, active galactic nuclei, which could be a black hole. So we don't know exactly the nature of these objects. We just know there are jets coming out, and it's highly very supermassive, and it's secreting material. But some of the galaxies, they lack anything at the center altogether.
Okay.
Some dwarfs, some So there are a lot of different classes of galaxies, and some of these have black holes.
So Milky Way galaxy has
Milky Way has a black hole, and the discovery was very interesting. You should read about it. I really like that's something one of my favorite parts of the subject.
Okay. What about during the black holes also means like in Einstein theory of relativity doesn't work at the black hole because it's like where there is like if you calculate via those equation, you will get an infinite amount of in terms of you get an infinite amount of space and time breaks at that point of means like I would say at the black hole. So there are no calculations at that point of time.
I think you're talking about singularity because that's the point. Yeah.
Even in the equation in engineering physics, we talk about this. When you plug in those black hole kind of situation, you will get singularity in the equations. That's why it means like it's difficult. So this was one of the intriguing thing which Einstein from this, Einstein came to know like by the interaction of two black holes, so like binary black holes. So he believed there may be an existence of gravitational waves as well. So that
Actually,
he theorized. Yeah.
gravitational waves was a theory. I don't think, I don't know, but about how he thought about gravitational waves. But yes, one of the parts of theory of relativity was prediction of gravitational wave, because he did not believe gravitation was a force. He believed that it's ripple in the space time. So he believed there's a space time fabric that exists, and if there is a ripple, if there is an activity, an object there, so whatever
Mass.
deformation happens,
Yeah.
mass, whatever deformation happens in the space time fabric, that's gravitational.
Yeah.
That gives rise to gravitation, and
Yeah.
it gives rise to gravitational waves. So one of the ways modern astrophysicists thought, if gravitational waves actually are what Einstein believed them to be, um, we could detect it where very massive objects are interacting with each other, like black holes and black holes and neutron stars. So these
Yeah.
are very massive objects, and when they interact with each other, there are high chances that the ripples will be generated in the space-time.
Yeah.
And the problem is, these ripples, by the time they reach Earth, they become so weak that it's very difficult to, detect them. But we did detect them with
Yeah.
very sensitive instruments
LIGO.
like LIGO, and one
Yeah.
more is coming, Virgo. And now we know that gravitational wave concept was actually true. Like Einstein was right about that.
Yeah, and they
So
got the Nobel Prize also for LIGO.
yes, they
It's
did.
like they made two different LIGOs at different part of the US,
Yes.
and how they made it at 90 degree. So how light stretches in one part as compared to other part if
The
there
other
is
part.
a ripples in the space time
Yes.
created
And
by
laser, they divide a laser and they send
yeah,
this
so they was
laser
like
in
90
two
degree,
different
so they
arcs.
divide a laser that is a similar laser that goes in two
Yeah.
different direction, and there is a
Yes.
reflection from that side. When they meet, if there is no ripple in space time, they should cancel out zero. If there is a resultant, if you remove out the noise, if there is sufficiently a resultant, then there is a existence of gravitational waves, and they made it two different places so that they can see similar effect on both the places. Yeah, on one is in east of US, one is in west of the US. And in 2019, a scientist from Georgia Tech, I don't believe where is from he got a Nobel Prize in 2016 or 17 for his discovery of LIGO. Yeah.
I think it must be after 2016, maybe 2017,
Or 18.
19?
18. Yeah, somewhere
No,
around that
19
time.
was Andrea Graz. Okay, yes, yeah.
2016, I think it's about topology, something like that.
It's
I
about
don't know.
topology. Huh?
Yeah.
It
2019
was theoretical astrophysics.
Yeah,
It wasn't in observational. So LIGO might have been after
Yeah.
2017.
So a lot of people explains this thing, this waves, like you drop a stone in a water and these ripples comes, and if you have an interaction of these ripples with an object, just a floating boat, just assume floating boat or a floating duck, choo 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 choo, that is towards the boundary, and how it deflects. So Earth will also be shaking when that happened.
Yes,
It's difficult
I
to
agree,
visualize
yeah.
that, but that is the similar
I think
example.
instead of thinking of it as like a water, like surface of water, what I like to imagine is it's a gel kind of structure all around you. So when you are in
Oh,
that, you're sending ripples in all directions. So
yeah.
I'm not sure. Someone who works in space-time can confirm that, but it does not have to be necessarily in just one direction, right? It has to be isotropic.
Yeah,
So
that's true.
it makes
It's
sense
isotropic.
to have to be, yeah.
Yeah. Isotropic, yeah, it need to be isotropic because depends on if you define isotropy. We generally define isotropy in materials, like different properties in different direction. And anisotropy is like when you have different properties in different isotropic, when you have same properties in all the direction.
In
But
all
I
direction.
assume vacuum is isotropic because
It has to be.
Yeah, it has to be.
Right?
Ether
Why
or
would there
whatever
be
the
a
concept.
preference for direction, like one direction as compared to the
Yeah.
others? It has to be isotropic.
Just assume we're talking about Earth vibrating because of this wave passing through it.
Yeah.
We will be
Yeah.
also vibrating.
Yeah.
Something
But
of
they're
that sort.
so faint vibrations, I think,
Yeah.
as compared to everything else that's happening, you might not even
Yeah.
feel it.
But there's means like some sort of, they're just like exaggerated version of it. But black holes are pretty interesting, I believe. But somewhere
Very.
down
Very
the line,
exotic objects.
they are very exciting objects. It's like in space time it's a fabric. So it's like if you assume that as a curtain, there are a lot of holes in the curtain. Some sort of means like it's like
Very
those
small
kind of
holes.
yeah
Yeah.
as compared to the I would say gigantic nature of the space time. These are very
Yeah.
small holes, and when there is a very big event happens, then I think that even they were talking about when they got the Nobel Prizes for it was 1.4 billion light year away, something of
Hmm.
that sort. There was a number related to billion years away that event happened where two black holes merged together, something of that sort.
Yeah.
Yeah. So it
Yeah,
was.
I think so. Since it was so far away, it must have been even fainter to detect. But
Yeah.
the marvelous thing is, we did, like on a small planet near a
Yeah.
very
Thanks to engineers.
regular star, thanks to
Yeah.
engineers, yes, and
Yeah.
scientists. But I really find it so fascinating that we are able to see all of this, interpret all of this, and so curious about the entire universe that it's impossible to imagine that we know all of this.
Yeah.
And it's all because, you are getting some photons from a very distant part of the universe and you are making sense of what you are seeing.
Yeah.
It's amazing.
And removing the zitteriness and other things we are also absorbing from the environment. So removing out the randomness and all. It's like
Yeah.
that is pretty means like I would say challenging and
Actually, I mean, if you read, like, you see the struggles of astronomers to just make sense of those few photons they are receiving, how to make the most of them.
yeah.
I've been there and I know, like, I spent more than half of my PhD just getting rid of noise from my data. It was so frustrating. And still, like, in the end result was reasonable, but I can imagine there are ways to make it even better. But there's only so much you can try. And with so many satellites launching into space now, like from Amazon and which is this company, Elon Musk company?
SpaceX.
SpaceX,
Yeah.
yes. So Starlink series of satellites. I do not know what's going to happen to astronomy in future, but it's going to be very frustrating for
Good times are coming, I
astronomers.
believe, if the wars are not
Well,
happening. Yeah.
I hope
If
so.
wars stop happening and there will be more collaboration, I believe, among scientists when they overpower the political ideologies of different countries. So there will be much more collaboration among scientists that can happen. So other thing which is more intriguing or I believe is fantastic, I have very limited knowledge of it. It's like dark matter.
Yeah.
It's like the entire, if you calculate the entire matter, weight of the mass of the entire matter, so it comes out less, somewhere like less. So rest of
Yes.
the matter is in the form of dark energy, dark matter. These are also some of the
Dark
facts.
matter is just the term they give. It's exactly what it says, dark matter. So it's
Invisible, yeah.
I'll tell you, it's an interesting story. So you know the Newtonian dynamics, where you can observe an object. You can predict the speed of an object at a certain distance, depending on the mass enclosed by that object, right? So we do the same thing for the galaxy. If you want to know this velocity of a star at certain distance, you just see how much mass is enclosed within that distance. And mass, by mass we mean visible mass, whatever you can detect as light,
Yeah.
because the stars all emit light, right? And that's what we were looking at: stars and gas and dust, all of these things. So there's this astronomer called Fritz Zwicky, and he was what he observed was this curve of velocity. So as you go farther away from the galaxy, this should drop.
Yeah.
But it was like at some point it was peaking and then it was staying constant. It was not dropping. So there was this discrepancy of the mass. Like, what we were looking at was the mass from which I was saying that the velocity of a star should be this, but it was higher than what I was
Okay.
predicting. That means there should be more mass in that galaxy than I am seeing. Yeah, so that's what dark matter is, and so far we don't know. Like, so far we don't know what is the nature of this dark matter. People still think it could be WEMP or like weakly interacting massive particles or axions, or things you cannot detect. But we don't know for sure what actually dark matter is. But we
Okay.
know that it exists. Something exists.
Okay. And another amazing thing about black holes and gravitational waves, sometime back when I was in India and there was this black hole research, there was some research going on in CERN. So there was a news in India that was very, I would say, funny. They were talking about when they were, doing collision of the photons in the CERN Large Hadron Collider. People were saying it will create a black hole. So that was a funny story. I don't know what's
I
behind
remember
that.
that from the news.
Yeah.
Yes.
12 बजे
It was.
दुनिया खत्म होने वाली है.
Yes. Oh my God, that hoax. It was on
Yeah.
news channels. It's stupid that I don't know. Yeah, but I think the thought came from the fact that they were trying to recreate what happens in the core of the sun.
Yeah.
They were trying to create these new particles by, accelerating particles and making them collide and seeing what comes out. So again, I'm not a particle physicist, so I don't know exactly what actually they were trying to create and what particles and
So they were
whatever.
trying to create what happened after Big Bang. So
What
what
happened
happened
after
after
Big
the
Bang?
Big Bang?
Yeah.
And what all
Yeah.
particles are created? So they want to validate their standard model of, I would believe, their standard model and of a standard model of quantum physics or standard model of the entire, I would say, physics. So they were intersecting. They were like, so they were accelerating the photons nearly the speed of light, and there were so many photons. They collide them, and they have different detectors to find out all the they. Once that was like Large Hadron Collider was installed, every week or every month there was a new particle discovery happening. So there was a joke in scientific community that it will be surprise when people won't get a Nobel Prize for a new particle. It was like that. There was
I
a
imagine
sometime.
because it's very it's fascinating to see that all these new particles being discovered. I think the Higgs boson particle that's the one I remember.
God particle.
Because yes, God particle, because that was theorized years ago, and now finally they were able to create it and validate its existence, which was
And the thing you were
incredible.
talking about randomness. So I was reading the mathematics of how they find out whether it's a Higgs boson particle or not. The theory behind everything is like when they were having a particle, both photon intersecting each other and having collision, there is 1/1000 1 billionth probability that there is a creation of Higgs boson. However, they made the adjustment in such a way that there will be like few number of thousands of photons that will be doing intersections, and they do this again. So in a year, there is a higher probability that we can hit a Higgs boson.
They're just increasing the likelihood of this event happening. Yes.
Yeah. And then since Higgs boson, there is no detector as well for Higgs boson, and so what they do, like Higgs boson, when it disintegrates into two photons, and however there are already a lot of photons, so how do you know that Higgs particle has created these two photons, so twin photons? So there is a lot of algorithm behind that. So there is an invariant mass concept. They calculate the invariant mass and then remove out all the possible possibilities. So that's what you are saying. So there is actually a curve. So when they show in whatever the Higgs boson discovery happened in 2012 or 13, so they were showing a curve like this, and there was a blip in the curve. So what is happening? These were just randomness. So it was, since it is a non-flat probability distribution, there is a higher probability of creation of some kind of photons as compared to other kind of photons. That's why it was not flat. It was like this, and there was a blip at 250. When they do all the randomness and all, when there was a blip at 250, and that was a creation of like Higgs. That proved existence of Higgs boson. However, the Nobel Prize, Higgs won it for Higgs field, actually. So Higgs boson are just the excitation of Higgs field. When you sit at the Higgs field, it creates a Higgs boson particle, and all the mass or all the interaction of particles with the Higgs field gives them mass. It's like what you told, a very good example. It's like a molasses. Higgs field is also a molasses. When the particle moves through it, it keeps on gaining. It gains mass. So that was.
So I did not know about this. That's very interesting. Like maybe I'll read about it.
Yeah, you read about that. Means like the main thing which I liked is the algorithm. So they keep on doing repetition experiment because they don't know whether the Higgs. That Higgs particle or Higgs boson particle was created or not, because they don't know the mass of also that. So everything was unknown in a way.
So was it also a relativistic particle?
Relativistic particle means?
Like the particle that has speed similar to speed of light.
So it is a relativistic particle, but they change the frame of reference in order to make it stationary.
That's what,
and
like,
that do,
if you want to actually get the true parameters, you have to change the frame of reference
yeah,
to
they
that
were
particle's
doing
frame.
yeah, and that they
Because
were
everything else
changing frame.
changes.
Yeah, they were changing frame of reference, and they did this calculations, and they find out later on. They find out the mass. They find out that it has spin 0. This was the first particle that they find out having 0 spin.
Okay.
And yeah, and they charge what is the charge of the Higgs boson particle. So they call it God particle because like similar concept, like it gives mass to everything, and mass is so fundamental to everything. Matter means like mass is so fundamental to matter. So it was very big discovery. So yeah, means like this fantastic research happens in astrophysics, and these days I don't know, means like previously it used to be, but these days I believe there are a lot of, do you know this Brian Cox, who is like a cosmologist from UK, and this Neil deGrasse Tyson, they do a similar kind of tour. You know, that tour that happens for Taylor Swift, Justin Bieber, that happens for them also.
They do a lot of science outreach.
And the Wembley Stadium, the Brian Cox, when he visited Wembley Stadium, that Wembley Stadium was fully filled. So you can assume the popularity of astrophysicists.
Yeah.
So the thing about what he research on is he has a new project. So he research about cosmic background radiation. So that is a word also we hear about. You will see a globe, sort of like orange kind of globe, bulge out of, and there are a lot of colors on there.
Yes.
Yeah, what is that? Means like cosmic background.
So cosmic microwave background is light from the early universe when the Big Bang happened. And so it's like Doppler's effect. When you go farther in space, the wavelength increases. So whatever the wavelength was, like from the predictions of Big Bang, what light would have been emitted at that time. So the prediction was, if you look at that light right now, it would be in microwave wavelength part.
Spectrum, microwave.
Spectrum, yes. Yeah. So do you remember when you were a child and there was, you were watching television, there was no disc on the television, there was, the noise and that black and white gray thing on the television?
Yeah.
That was cosmic microwave background because it's hitting everything all the time. It's coming from the space and it's all the time there. So the discovery was also very interesting of CMB. It was theorized years ago. Astronomers told you should be able to have.
I think
Big Bang happen. Yeah.
All the science happened around 1950. After that, there is no science happening. That's
not really.
I believe that's now engineering. Proving
now we are making the discoveries. Yes, they predicted it then, and now we are just sitting.
Thank you to engineers like me who are doing this incredible work.
Yes,
from Rashi, I believe, and their community.
Thank you so much, Mahinder, for being an engineer. But yes, so actually this was discovered by two radio engineers. There was a problem in some instrument, and they were there to repair it. And they couldn't estimate where that noise was coming from. So they thought it was from pigeon poop. So they cleaned all the poop, and still that noise was there. And this news traveled to the the observatory people that there is something like this, and these people are facing this problem. So they called up and they asked these engineers, like, what exactly are you listening? And what is the nature of this noise? And they explained, and they were like, okay, I think we have discovered cosmic microwave background. And then they went on and measured this, and then that was when it was confirmed that Big Bang, like another step towards the confirmation of Big Bang, that Big Bang happened. The light that is coming from the early universe is actually in the cosmic. So the map that you see, the map that you said, like the globe kind map, it's basically all sky map. So all sky map, so it should come from everywhere. It should be isotropic. And there's another thing in cosmology that talks about formation of fragments in the early universe because of whatever. So this microwave background also is not like uniformly distributed throughout the space. It's coming in fragments, where, so that's why you see those structures. So all of this is confirmation about Big Bang and what we are looking at right now.
So a lot of people say is that, like a lot of physicists like Roger Penrose, he also got for Penrose.
Yes.
He got recently his mathematics work at Cambridge. He got a Nobel Prize for that. However, he believes that Big Bang was just a concept, but it never happened, because he thinks about this aloneness which I was talking about initially. He exaggerated and he take back, and he says how Big Bang happens. So he says when space is stretched out so much and there's no even a photon particle existing, it may happen at some point of time that all the star will get dimmer and dimmer and dimmer, and their light will not be able to, there was not even a single existence of photon. Then he talks about the main intricate part, how Big Bang starts. So he talks about like from some wormhole, there's one photons comes out, and then he talks about that. I also don't understand, but according to him, it's a continuous phenomena, creation of Big Bangs and all, and how these events keep on happening. So this is just a theory from his side, but this is very, I would believe, very intriguing.
Okay, I have not heard about this theory, but yes, I think there are so many theories around, because we don't know what's going to happen. There will be a big crunch, or the universe will keep on expanding like this. So maybe one of those theories that thinks about how things will end or if they will not end, I think.
Do you know around the big crunch there is a movie? You know what happens? No. So there is some forward in time happens. Forward in time. So they are showing a movie or some kid moving, all around random videos they have shown. Then big crunch happens. So what they are showing, all the videos, they are moving backwards. So what happens? So they are saying arrow of time is reversed. So everything is like reversing in some or other ways, you know.
What is this called? What is this movie called?
I don't know. Means like I will put the picture.
Search.
So it is like all the people are moving like this. All the entropy is also reversing. Now what happens right now? Entropy drives the universe, and it's like randomness. So now everything, don't try to be reverse entropic. Everything is reverse entropic because the arrow of time has changed. So they are moving this fantastic, means like they made a very good videography. Means like it's like a very boring movie. So it's around big crunch, you know. Everything is reversing in time. So they have, you know, changed the arrow of time. They have changed this entropic principle and all these facts. So these are very amazing things, like around Big Bang also. So these are the things which, like, with more discoveries and more technologies, more data processing algorithm like AI and all, when they come into picture, and things, you know, proportionally, we see, like, if we see, there's one problem with a lot of people. We human as think as a linear being. Our thinking is linear. Okay, आज 2 दिन में, in 2 days this happened, so next thing will happen in 4 days. Like how we linearly map. However, technology is so non-linear, because what happens, all the components will be parallelly researched on, like how sensors are getting smaller, data processing algorithm is getting better and better, and even all the things, you know, overall global GDP is increasing, so there are a lot number of engineers putting their head. So this is how the exponential thing, maybe in 50 years will be much more in the astrophysics community, like your and astronomy. There will be much more discoveries.
Exponential, the growth, the discoveries, the contributions. I think it's going to be a very exciting time for not just astrophysics, I think technology and everything.
Yeah, that's
the speed we are going at.
आपका बहुत शुक्रिया हमारे पॉडकास्ट पे आने के लिए. Very thank you so much, and your presence will enlighten this conversational podcast. Thank you so much.
Thank you for inviting me, Mahendra. It was like a very good conversation. I thoroughly enjoyed talking to you.
Yeah.
And learned so much from you. So, yeah.
Please say to the audience, like, if you like this channel, subscribe it, because they are so fantastic, you know, conversation, you know, still.
Yes, they are actually.
Yeah.
They are very interesting conversations. You get to learn, but you won't realize. Subscribe to, क्या नाम है तेरे चैनल का?
Mahindra podcast. Mahindra Rotela.
Mahindra Rotela's podcast. Yes.
Yeah. See you. Bye.
Bye-bye.
Bye.